Good morning, my dear students. Let's continue the chapter Magnetism and Matter. We have almost come to an end for this chapter. Let's see. The last concept in the last session, majorly we had discussed related angle of dip. Out of three important elements in Earth's magnetism, so this is one of the very important element of Earth's magnetism, right? Which we had discussed the second one, all right? Angle of dip. So this is also called what we had discussed, a magnetic inclination. Clear? Denoted with the symbol theta, delta. Theta was magnetic declination. Okay. And this angle of dip can also be called as true dip. What is this? True dip. Now the major part of the session will be related to apparent dip. Look at here. What is this? Apparent dip. And this apparent dip is also called as false dip. What is that? False dip. So this is denoted with the symbol delta dash. No confusions at all. Delta dash. So for most of the students it will be a difficult topic. That's the reason they leave it. But there's no need of leaving this small topic. How easily we are going to discuss about this apparent dip or false dip. Let's check. What exactly meant by the angle of dip? I'll just remind you once, then we'll move to the next sessions. We all know that this is called your magnetic meridian. Okay, I'm just imagining that this is my magnetic meridian. In this magnetic meridian, if I keep a magnetic needle here, what happens? It will dip. That means it will fall and come to rest at a particular angle with this horizontal Earth's magnetic field. So that is called, this is the final magnetic field due to the Earth direction, it will be aligned. So this is called angle of dip, as it is Earth's magnetic field P, and this is called horizontal component of Earth's magnetic field, which is a B cos delta. And this is the vertical component of Earth's magnetic field, so that also we know, which is a B sine delta. No confusions. This is called angle of dip, we know. That's called true dip. At any place, if you keep a magnetic needle or magnetic compass in the magnetic meridian in this way, it will fall and stays rest at a particular angle with a horizontal component, and that's called angle of dip. Then what is this apparent dip or a true dip? And it is not compulsory that always we need to keep a magnetic needle in the magnetic meridian. So again I am telling you, so this is called a magnetic meridian. And in reality, generally speaking, in reality, and we don't know and we will never be knowing that which is the magnetic meridian exactly. Magnetic meridian either in this way or in this way or in this vertical plane. We don't know exactly. So that is why, look at that, a very important topic here. Any other plane, for example, in any other vertical plane, if you keep your magnetic needle, that will also show some dip. So that is called apparent dip. That's called what? Apparent dip. Imagine there is another vertical plane is considered. So the same plane is turned at some angle. Look at here, this is the angle called theta. At some particular angle, so this magnetic meridian is turned. So look at here. This is what the another vertical plane, a random one, a vertical plane is considered. Here if you keep the magnetic compass and it will be dip. So that's called apparent dip. What is this? Apparent dip will appear in this vertical plane. So to find this apparent depth, three physical quantities or two quantities are very important, and the number one is true dip you should know, and how much angle between the magnetic meridian and the considered vertical plane. So these two are very important if you want to find this apparent dip. Okay. So the derivation is not required for us. Even for your board exams also it is not required for us. So that is the reason I am just going to give you a formula. So what is that formula? Tan delta dash. What is delta dash here? Apparent dip. Tan delta dash is equal to tan delta divided by cos theta. Remember, tan delta dash is equal to tan delta by cos theta. What is this? One by one. What is this delta dash? Delta dash is apparent dip. What is this delta? That's called true dip. See here, angle of dip or true dip is delta. And theta. Theta is clearly mentioned here, the angle between the magnetic meridian and the vertical plane. I am writing here, theta is the angle. And before that, let me box this, a very important formula. So theta is the angle between a magnetic meridian and a vertical plane. Alright. Now, how the numericals will be asked, and let's see. You'll understand the complete picture now, but try to remember this formula instead of deriving it. The true value of dip at a place is 30 degrees. True value of dip. So given value delta is equal to 30 degrees. True value of dip. The vertical plane carrying a needle is turned through 30 degrees from the magnetic meridian. You got the point? From this magnetic meridian, the vertical plane turned through an angle 30 degree. So that is called theta is 30 degree. Understand? That's not the apparent dip. That's just an angle between the magnetic meridian and the vertical plane. Now the question is, calculate the apparent value of the dip. Find delta dash. Just use this. Tan delta dash is equal to tan delta. What is that? 30 degree divided by cos theta, which is cos 30. Okay. Tan 30 value is 1 by root 3 divided by cos 30 is root 3 by 2. So what I can write, 1 by root 3 into 2 by root 3. This root 3 by 2 goes to the numerator. So that will be 2 by 3. Tan delta dash is equal to 2 by 3, and I can write your delta dash is equal to tan inverse 2 by 3. That's it. That is the answer. You got the point? Everyone. So is it simple now? It's so simple just because we have remembered the formula. Alright? So this is required. Even in the NEET exam, that the expecting level of asking this question is very, very, very less. The chances are very less. But try to remember the formula so that you can answer if this question comes. Now, see the another one. You get a clear picture now. A magnetic needle is free to rotate in a vertical plane which makes an angle 60 degrees with the magnetic meridian. What is the theta here? Theta is clearly mentioned, it is 60 degree. Okay. Now, if needle stays in a direction making an angle of tan inverse 2 by 3 with the horizontal, what is this value? Is it apparent dip or actual dip? Tell me. Definitely it's an apparent dip because it is happening in the another vertical plane, which is at 60 degrees angle from the magnetic meridian. I hope, my dear students, you're getting the situation here. So your theta is 60 degrees, apparent dip. Delta dash is equal to, what is that? So delta dash is equal to tan inverse of 2 by 3. Okay. So from here you can also write what is tan delta dash? 2 by root 3. Obviously, I hope you understand what to be find out now at the end of the question. What would be the dip at that place? What is the right dip? What is the exact dip or actual dip or called true dip? No confusions at all, right? Only three unknowns, 1, 2, 3. If 2 you know, then the other one you can easily find out. And let's use the formula. Tan delta dash is equal to tan delta by cos theta, and tan delta dash is equal to 2 by root 3, which is equal to tan delta. What is tan delta here? That is what we need to find out. Tan delta by cos theta, which is cos 60 degree. And this I can write 2 by root 3 into cos 60 is 1 by 2, which is equal to tan delta. So 2 cancel. Tan delta is 1 by root 3. Tan delta will be equal to tan. So what is that? Delta is equal to tan delta is 1 by root 3. Okay. So delta is equal to 30 degrees. Tan 30 is only 1 by root 3. So that's what we have done here also. Tan 30 is only 1 by root 3. Got it? Clear? In NEET 2017, there was a question based on this. NEET 2017. So it is a statement given, a direct question. What was that question and how to solve that question we'll discuss here itself. Question is so simple, similar to this. There are two vertical planes perpendicular to each other. Imagine it's a vertical, they're not the magnetic meridian. Understand? There are two vertical planes. It is first vertical plane and the other vertical plane is like this. So this is another vertical plane. In these two vertical planes, apparent dip values are delta 1 and delta 2. Simple. These two vertical planes are perpendicular to each other. Okay? Perpendicular to each other. Now, actual dip is delta. Actual dip is delta. Now, the relation among these three quantities they are asking. So, the relation among them will be cot square delta 1 plus cot square delta 2, which is equal to cot square delta. Okay, my dear students. Again, I am telling you the very important case. In NEET 2017, this is the question asked. Simple. There are two vertical planes which are perpendicular to each other. In each vertical plane, there is an apparent dip value which is delta 1 and delta 2. Of course, in the magnetic meridian, what is the actual depth? That actual dip, that is delta. The relation among these three will be cot square delta 1 plus cot square delta 2 is equal to cot square delta. Okay, clear? So remember this equation and this equation. Other than this, no question will be asked in the NEET exam or JEE exam or even CET exam also. Alright. We'll move to the next topic. Well, my dear students, now the topic is neutral points or null points. So simple. Null or neutral means what? 0. What is 0 here? The points in a region or a space. Those are the points in a region or a space where the resultant magnetic field is 0 or cancelled. Okay, so these are the points are called null points. The probability of asking a question in your NEET, JEE or CET exam on these topics is very, very, very less. But still, we are not neglecting any of the topic. Let's see the neutral points. In connection with Earth's magnetic field. So this is what we are discussing here. Neutral points in connection with Earth's magnetic field. Okay. Now, look at the situation, the first case. Imagine the bar magnet is kept in this way. So this is a north pole and south pole. For your better understanding, so this is north, south, I am talking about geographic, north, south, east, west. So the north pole of a bar magnet is placed in the direction of geographic north. Now, you know how the magnetic field lines will generate here. Magnetic field lines outside the magnet, they move from north to south. Inside the magnet, forget about it. So here also outside the magnet, they move from north to south in this way. Okay. So for example, I am just imagining that the magnetic meridian, so this is what placed in a magnetic meridian, and the magnetic field lines, earth magnetic field lines. So earth magnetic field line means the horizontal component of earth's magnetic field lines are moving in this way. Actually, in reality they are not straight, but for your better understanding, I am just drawing them straight, no confusions. Okay. Look at the situation. So another magnetic field line I am just considering here. You can see the another magnetic field line I have considered here. How? Outside the magnet they move from north to south. Outside the magnet they move from north to south. Look at the two places. On the axial line of this magnet you concentrate. On the equatorial line of this magnet you concentrate. This is the midpoint of the bar magnet. At what point the net magnetic field can be zero? On its axial line or equatorial line? Let's concentrate on axial line. Axial line, what happens? You can see the Earth's horizontal component, I am writing here BH bar direction is like this. So it's a BH bar direction is like this. Look at here. At this axial line also the BH bar is directed in this way, whereas your magnetic field lines due to this bar magnet also moves in the same upward direction. Okay. Here you can see BH bar is directed in this way. At this point on the axial line your magnetic field lines are moving in the same direction. Then the resultant magnetic field will be the addition of the magnetic field due to this bar magnet and this horizontal Earth's magnetic field. So is there any possibility of getting the resultant magnetic field is zero on the axial line? Impossible, right? Now the possibility is there on the equatorial line. Look at here. Here at this point, imagine a point. Because of the bar magnetic field lines, you can see it is B bar is in this direction, downward direction at this point. At this point, imagine it's N, neutral point N. At the same point, Earth's magnetic field is moving upward. Magnetic field due to this bar magnet is moving downward. Okay. There is a possibility of getting the neutral point here on the equatorial line. Imagine this is the neutral point on the equatorial line is at a distance d from the center of the bar magnet. Okay. So now on the axial line, so magnetic field due to this bar magnet on the axial line, so we have the formula. What is that? So B is equal to mu naught by 4 pi into m by d cube. What is this m? M is magnetic moment of this bar magnet. Okay. Clear? At the same distance here also there will be another neutral point N1 and it's imagine N2. Alright? N1 and N2 are the neutral points here. Okay. Now the next case also you can understand. What is the next case here? This is a south pole and north pole. Let me just interchange this. Identify, see, you can consider the same. Earth's magnetic field is in this direction itself. Actually, I'm telling you once again, in reality it will not be like this. So this is Earth's magnetic field, horizontal component of Earth's magnetic field, BH bar. Identify in this case. Identify in this case where the neutral points will be. Either on the axial line or on the equatorial line. If it is on the equatorial line, you know at that particular point on the equatorial line, magnetic field due to the bar magnet formula you have. In the same way, whatever the point you get, which is the neutral point, you try to write the magnetic field due to the bar magnet at that point. I hope you got it, right? So this is the formula what I wrote. This is the formula of magnetic field due to the bar magnet on the equatorial line. If you get your null point on the equatorial line, your formula will be same. If you get the null point on the axial line, your formula will be different. Write down. Just pause the video, draw the diagram neatly, write the equation properly, identify the null points N1 and N2, just send me a WhatsApp message immediately. Okay. Now, third case is also there. So, I'm just rotating the bar magnet in this way according to the geographic axis. You can see, I'm just keeping the bar magnet in east-west direction in this way. This is north and this is south. Identify the null points here. I'm just keeping the BH bar in the same direction. BH bar in the same direction. I'm not changing the Earth's we cannot change Earth's magnetic field direction. Clear? Here also find the null points here, N1 and N2. So just turn this magnet, the fourth case, turn this magnet into the other way. So this is south and this is north, and Earth's magnetic field will be the similar. Identify the Earth's magnetic field, identify the null points, these three cases, and write the equations similar to like this. Then send me immediately. My dear students, so these are the three class work questions. Other than whatever I had just given you to do to draw some kind of diagrams related to the neutral points. Other than that, these are the three additional example questions you have to solve now, right? So remember, these are the class work questions only. After the class, your 5 questions will be there as usual, right? Now, look at this. In all the questions, there will be a word called dip circle. Dip circle is an instrument which will measure the angle of dip. Understand? In any meridian, that may be the magnetic meridian, that may be in the vertical plane. The dip circle is just a device or instrument which can give you your dip value. Maybe the actual dip or apparent dip. In everywhere you can see that. So what I just wanted to tell you is, pause your video here, read all the questions, answer them, send your solutions immediately now. Don't take much time. And your assignment questions also will be similar to this. Before solving this, just revise the previous things what we had discussed today itself. Right? Just the previous 2 slides. Just go through them, solve according to the formulas mentioned in your notes. All the very best.